Hey everybody, welcome back. Good to see you again. Mr. Smith here. In today's slide deck, I'm going to give you all of the basic formulas that you need to handle mechanical waves. So to begin with, this one isn't really even a formula. It's just a skill that if you don't follow along completely with what I'm doing, I want you to shout out a question in class when you see me so we can stop and explain it further. Counting waves is really basic. So sometimes you'll get graphs like this where I have distance and distance on the graph, and so I'm looking at a map of how the wave spreads out over space. So how many wave cycles are shown? For me, it looks like this. Wave begins here. That's the halfway mark of a cycle. One complete cycle is from here at 0 mark till out here at 4 meters, which incidentally is going to tell me that the wavelength of this wave is 4 meters. So if I follow the whole question through, how many wave cycles do I see? I see one other complete wave cycle out here at the 8 meter mark, which it all makes sense. So I see 2 complete waves in this diagram. They're not always going to be that easy because sometimes they'll give you a fraction of a wave and you have to know what to look for. Okay, so anyway, finally, what's the amplitude of the wave? Amplitude is just the height from the midline to a crest or the midline to a trough. So either way you slice it, it looks to me like that's about 1 meter from the baseline to the top of a crest or the baseline to the bottom of a trough, okay? So I said something about fractional wavelengths. So this is the other kind of graph for transverse waves, right? They have displacement up here, which is amplitude, and they have time here, which is different than distance. So to count the waves, we'll start just like we did here at the 0, and we'll go 1 complete cycle is from here to here. 2 complete cycles is going to be here, and then this will happen sometimes. I'm going to get 2.5 cycles, or 2.5 waves in that space, okay? That's important because when they ask me things like period and frequency, there's going to be information on the graph about time. So I have sort of a built-in fraction here. You remember how period is the time for the wave to repeat once. Well, what I've got in this example is I've got 25 seconds, so I'm going to put time on the top, over 2.5 waves, and when I do the math there, I'll get 10 seconds per 1 wave. Okay, so that's what the period is. It's the time for 1 wave. Just make sure you've got the time on the top, and it'll probably come out fine. So frequency, as you remember, is the reciprocal of period, and what I do is just flip this fraction upside down, and I could do either 2.5 over 25 seconds or 1 over 10 seconds. And if you're paying attention to labels like you ought to be, you'll notice there's no label in the top. So you can think of it as cycles or waves, but those aren't really physics labels. Those are just a counting thing. So what I get when I have 1 over seconds is, once we get the number part out of the way, hertz. Hz, our unit for frequency. Okay, so having said that, let's dive into the actual formulas you're going to use and get moving. So the first actual formula is one that we use to talk about how waves travel out in the real world. So just like you throwing a baseball, if you shout, then air molecules will carry the energy of your voice out into space. So the thing is that because the medium, the thing that's waving, determines the speed of the sound, we get to use the easiest formula in physics. The way that waves travel is distance equals speed times time. That's our constant speed formula. So what's an actual question that you'll have to deal with? It's kind of one like this. So because air is the medium for sound, and air can actually vary a little bit depending on temperature and humidity and different stuff, this number, 340 meters per second, can vary a little bit. But let's just go say it's 340 meters per second today. A boy stands 100 meters from a wall and shouts, and they want to know how long will it take the sound to reach the wall. Easy, right? Because we know the speed is constant, we can use our constant speed formula, d equals v times t, and just solve that for t. So t will equal d over v, and we'll just write it like this. So d is going to be 100 meters. The v is the speed of sound, 340 meters per second. You do the division, and you get 0.0294 seconds for the time it takes the sound to go to the wall. So what about part 2? When will he hear the echo of his voice? Well, if we assume that this kid has no reaction time delay in his neuroprocessing, then the time for the echo is just twice the other time, right? That's important because you're going to have to read questions carefully to make sure what kind of information they're giving you. But in this case, it's super straightforward that if it took this long, 0.0294 seconds, for the sound wave to travel out, it's just going to take twice that long, 0.0588, for the sound waves to travel there and back. Okay? So example number 1, D equals V times T. So the next example is a formula that comes to us from the 1700s where physicists figured out, theoretically, what should the speed of waves on a slinky or a spring be? And we've got some pretty cool slinkies, and we're actually going to test this out in the lab. So what you do is you stretch out the slinky with tension. So you use a force measuring device, and you get, let's say, 12 newtons of stretching force. And then you measure the length of the slinky, and you get its mass. Make sure you convert that bad boy to kilograms, and then you just plug it in. So let's go see how this one works. So we've got tension is going to be 12 newtons. We're going to divide that, and I'm a big fan in your calculator of making sure you open up a parenthesis. So I'll type in 12 divided by parentheses 0.45 kilograms divided by 5 meters, and then close the parentheses and hit equals. And then once you're done with that, you can go ahead and throw the square root symbol at the thing. And if you do it all right, you should get 11.6 maybe meters per second. So if you didn't do it, then what I want you to do is pause the slide deck and plug that into your calculator. Make sure you actually get that to work. That's an important little small scale. So when we actually go to the lab to test how fast the slinky waves really go, what we're going to do is to fall back on our very simple formula. Distance equals speed times time. And we're just going to solve it. V equals D over T. So we're going to measure the distance between people, the time it takes the wave to get from here to there, except here's the deal. The time it takes to get from here to there is so quick that it's difficult to time it accurately. And so, as we said in our first slide deck, we're going to often try to make use of 1 round trip or 2 round trips, even if we can do it in the lab, to make sure we're getting the best possible measurements. So if your pulse will sustain itself, meaning you can see it clearly, and it will go 1, 2, 3, 4 between the two of you, that's 2 round trips. So just make sure that you're appropriate when you use distance and time. So if we're talking about 2 round trips, and that's the time you're able to get, that's actually going to be, for this example, 4 times 5 meters, if you think about it. If these two people are separated by 5 meters, right? So if that's the measurement that you made, and you plug in 20 meters over 1.9 seconds, you're going to get that the speed of the waves is 10.52 meters per second, which would be a pretty decent result, okay? And that brings us to our final example. This one's called the wave equation. The pieces of it you've already seen before. So V is the velocity of waves, Greek letter lambda stands for wavelength, and F stands for frequency. So here's a typical example. A student estimates a distance between crests of 20 meters. She counts 15 waves in a time of 30 seconds. How fast are the waves going? So you just need to know what things mean. So the distance between crests of 20 meters, that's the wavelength. So wavelength equals 20 meters. So if she counts 15 waves in a time of 30 seconds, I can use that information to make a fraction either to figure out period, which would be 30 seconds over 15 waves, or frequency, which would be 15 waves over 30 seconds. And when I do that, I'm going to get 0.5 hertz for my frequency. And then so all I need to do to get the speed of waves is just go ahead and plug these two guys together, 20 meters, 0.5 hertz, and I get a pretty realistic number for the speed of ocean waves in shallowish water, okay? So final example, ocean waves aren't the only things that can carry wave energy. Air can carry sound, right? So what happens when you ping a tuning fork is that it pushes and pulls on air, and so it creates areas of higher density and areas of lower density. So you should think back to our slinky examples and say, that sounds like a longitudinal wave where I'm squishing and pulling apart the medium. Aside from that, the math is exactly the same. So a tuning fork vibrates at a frequency of 440 hertz. Wow, no wonder it's hard to see these things vibrating. They're really quick. The speed of sound is 335, so again, around 340, but it can vary. So how long does it take for the tuning fork to vibrate one time? So just have to bear in mind. So frequency was 440 hertz. And if they wanted us to give them the period, that's easy enough. We just take the period and flip the frequency over. So 1 over 440 hertz is going to give me 0 point tiny 0.00227 seconds, which is like 2/1000ths of a second. So yeah, no wonder you can't really see these things vibrate. Finally, what's the wavelength of the sound waves? We just take our V equals wavelength times frequency formula and solve that for wavelength. So V over F is just going to be 335 meters per second over 440 hertz, the frequency. And that should work out for us. So we're going to get 0.76 meters. So the distance in the room between those pushes on the air is going to be around 3/4 of a meter. Okay, so those are the basics. Those ought to get you started and carry actually quite a long distance. Bring questions if you've got them. Great to see you and have a super day. Thanks. Take care. Bye-bye.